In this example, we're going to be finding a basis for the row space, a basis of the column space, a basis for the null space, as well as the rank and nullity of the following 3x4 matrix. Now, the 3x4 matrix has rows 1, 4, 2, 1, 0, 1, 1, negative 1, and negative 2, negative 8, negative 4, negative 2. Now, if I'm interested in the row space, I'm going to need reduced row echelon form of this matrix. If I'm interested in the column space, I'm going to need reduced row echelon form. And if I'm interested in the null space, I'm going to need to augment with zeros and then take it down to reduced row echelon form. So regardless of what I'm doing, I'm going to take this matrix down to reduced row echelon form. Now, I know that when I augment this thing with zeros, it's simply going to give me an extra column of zeros. So here's what we'll do. I'm going to do this without the extra column of zeros, and then just add in the appropriate column of zeros at the appropriate time. Now, even though I'm fairly confident that I could do this without a calculator, I'm still going to do it with a calculator. I'm pretty sure the operations would be do 2 times the first row and add to the last row to wind up with a row of zeros, and then take negative 4 times the second row and add to the first row. But let's go ahead and be as specific as possible, and it'll be good practice for my students to see this done on a calculator anyway. We'll go ahead and edit ourselves a 3x4. First row is going to be 1, enter, 4, oh boy, I messed up, hang on, okay, 3x4, okay, 1, enter, 4, enter, 2, enter, 1, enter. Second row, 0, enter, 1, enter, 1, enter, negative 1, enter. Negative 2, enter, negative 8, enter, negative 4, enter, negative 2, enter. Okay. Then re-enter the matrix menu, arrow over to the math menu, select RREF, then select my matrix that I refer to as A. I don't believe we're going to get any fractions, so no need for math enter on this one. So we'll take this and put it into our reduced row echelon form. This is 1, 0, negative 2, 5, 0, 1, 1, negative 1, and 0, 0, 0, 0. So to give this a full interpretation, we are first going to start with the basis of the row space. The basis of the row space is going to be the 2 vectors that we see from reduced row echelon form. So that'll be 1, 0, negative 2, 5, as well as 0, 1, 1, negative 1. For a basis of the column space, we note that it is only the first 2 columns that contain a lead 1, which means that we are going to go back to the first 2 columns of the original matrix A. Those 2 columns will form the basis of our column space. So those vectors are 1, 0, negative 2, and 4, 1, negative 8. The other 2 columns of the original matrix can be written as linear combinations of just these 2 vectors here. Now, both of these imply the same thing. The basis of the row space and the basis of the column space determine the rank of the matrix. The rank is defined as the dimension of the row space and the dimension of the column space. The dimension is uniquely determined by the number of basis vectors in the row space and in the column space. Both of these contain exactly 2 vectors, so that is going to wind up being our rank. Now, in terms of the null space and the nullity, we will need to interpret these 2 things in terms of A times vector x is equal to the 0 vector, where vector x, given that A is a 3x4, will have to have size 4x1. As such, vector x will be part of R4. Now we can just go ahead and interpret the 2 rows that we got from up here in terms of these variables by labeling column 1 as x1, column 2 as x2, column 3 as x3, and column 4 as x4. Now, keeping in mind that we're augmenting this with the 0 vector, the first equation would be x1 minus 2x3 plus 5x4 is equal to 0, and the second row would be representative of x2 plus x3 minus x4 is equal to 0. This tells me that the lead variables are going to be x1 and x2, and here we'll have two free variables in the form of x3 and x4. So we will assign x3 is going to be equal to s, and x4 is going to be equal to t. Then in terms of these variables, what we're saying is that x1 from this equation is going to be equal to 2x3, so 2s minus 5t. Then the second equation tells us that x2 is going to be equal to negative x3, so negative s, plus x4, so plus t. So this means that the null space itself would take the form 2s minus 5t, negative s plus t, free variable x3, free variable x4. Now, if we decompose that into a linear combination where the scalars are s and t, that'll give us our basis. So for the basis, we can get one of these vectors by setting s equal to 1 and t equal to 0. If we set s equal to 1 and t equal to 0, that will be 2, negative 1, 1, 0. If we set s equal to 0 and t equal to 1, we'll get negative 5, 1, 0, 1. Because there were two free variables, this also lets us know the dimension of our null space, referred to as the nullity of the matrix, is going to be equal to 2. The dimension of the null space is the nullity. There are two vectors in the basis, therefore the dimension is 2.